Hello everybody, it's Adam Bird, 973 Ramp again, and today we're going to be looking at a way that I like to model motion and design systems in one sketch. So one thing I like to do is actually design kind of the whole robot in one sketch, and we'll do that. We'll do another video on that. But I got some more immediate demands for this kind of thing, and instead today I'm going to focus on designing a rotary mechanism, which is a linkage, off a pneumatic cylinder, and how we space that kind of stuff. I've got a method there that I think is pretty clean. This is something I've iterated over time, but it's certainly something that if you feel like you have a better way of doing this, let me know, because this is the kind of thing that I always like improving on. I used to do this much worse in the past, and I do it better now. So I actually kind of like, in this case, to start with like a ground, and I'm going to draw a fake robot, something real ghetto. The origin won't be placed nice in this sketch at least. Let's say it's 32 inches long and we got a 2-inch tall frame and nominally 4-inch wheels, so we're an inch off the ground. And then we'll put some bumpers in just to get it to start looking like a robot. Collinear equal, equal. Ah. Bumpers 2 inches off the ground. I think we'll go with that. Click the wrong thing. And use this tool, 2.5 by 2. That's the sketch fillet tool. Select these guys. Boom. Now we have a ghetto robot with bumpers on it. So let's say we wanted some arm to go from, inside the size box to yay there. And we'll define this a little more. And we want to use a pneumatic cylinder. So what some people might do is dimension a hole on this arm and a mount point for the cylinder and keep iterating the cylinder until you get the motion you want. And I say, I have spent a lot of time doing that, and it makes me hate myself, and now I have a better way of doing things. So what I like to do is, instead of pick holes and see what the resultant motion is, I won't dimension where the holes are for moving stuff. I will dimension the motion and let that pick the holes for me. So you're going to have to use your imagination, because when I first start these things, I started all with lines, and then once I get things finished up, I'll make a line a rectangle to show tube and that sort of thing, but I always start with lines. So let's say this arm is 14 inches long, and we want it to be, at least the center line of that arm, 2 inches within the size box to start, and vertical. It doesn't have to be vertical. It could be an angle we dimension to. Maybe we could put the bottom at 2 inches, the top at 1 inch. Anything you want. Let's say you want that pivot 6 inches off the frame for now. You'll see we do have to put in some information, obviously, because it won't design mechanisms for you. And let's say we want this horizontal. We'll go with horizontal and make it easy. So perfect 90-degree motion. That can be kind of hard to get. So next would be pneumatic cylinder. So we can model pneumatic cylinder as this essentially. This is it extended, this is it retracted. So I'm not going to go through the Bimba catalog right now and go to McMaster and pick out a clevis and all that stuff. But we'll just make some assumptions kind of. Oh, actually, I kind of like a better way to model cylinders. Oh, no, I'm a hypocrite. I have a better way. So if you look at within a line of cylinders, there's essentially a couple base numbers. You have the cylinder, even with 0 stroke, has some length. And that includes your clevis length. So let's say we're doing 3/4 bore cylinders. I'll call that nominally 5 inches. So this is the length of the cylinder that happens no matter what, regardless of stroke. And then it gets longer, the body of the cylinder gets longer per each inch of stroke because you need that room. So let's say we're dealing with a 4-inch stroke cylinder now. Well, and that's retracted. So you have the retracted body of the cylinder plus the stroke length. And if you don't believe me, maybe I'll do a video just on using the Bimba catalog and stuff because that can be kind of tedious. And then these two are actually equal to that. So what you end up with is you've dimensioned the kind of base length of the cylinder doing some math. You looked up that a 1-inch stroke cylinder was, or actually the catalog's really nice. It actually says, 3.96 plus stroke. So that 3.96 plus whatever our clevis length is, clevis being the guy you screw on the end, gets you this 5. This 4 inches is your stroke, and this is your longer cylinder where you've extended by stroke. And what's clean about this is now you have 2 parameters to control, and you could even put this in a design sheet and drive these dimensions. This is a function of your clevis and your cylinder diameter. As you go to the next cylinder diameter, this will get longer because things get bigger, and this is a function of stroke. So you can more quickly iterate your cylinders. This is a trick I kind of learned after I did this whole process, saved me a lot of time, because now you can change a 7-inch stroke cylinder with the minimum number of dimensions, and you don't have to like do mental math and go like, oh, it's 3.96 plus 0.75 plus 7. No, you just got this. So let's say I want to mount the pivot of this an inch off the deck, because that's an easy thing for me to make. If I had to make it taller, that'd be bad. I can already kind of see that that's not good. It's kind of too low, probably. So the more logical assumptions you can make before you start stuff, the better. Although actually this might work, so we'll run with it. So what I do now is I make a set of attachment points, kind of, and I draw these off to make it easier to make them equal. And you'll see what I'm doing in a moment. And I'll say this process, by the way, can be extended to kind of any level of complexity as long as you are willing to do it. It can get kind of crazy though, but this is nice. You can do uneven 4 bars, you can really do anything. So now I make these coincident. So now you can see I have this pivot point that moves in relation to both arms. Here's the danger though, watch this. That crossed over, the other one didn't. So you got to watch out for that, especially as you get near 0. So like I said, logical assumptions will be real helpful from the get-go. So you can see, boom, now we actually have a partially defined working thing. And you can see the short stroke has it up and the long stroke puts it out. But it's still free to move. So there's other dimensions we would want to do. One dimension I like to play with is actually the lever arm you're acting on. And that's the perpendicular distance from your pivot point to there. And maybe that's something you want to maximize. And what you can do is like make the lever arm for one a driving dimension and make the lever arm for the other a driven dimension, and maybe compromise on those. So go, oh, I want this to be a little bigger to drive those more even. Wow, that looks pretty even. And sometimes actually I like to come in as well, although since I already mated that stuff and make it tedious, and draw a third arm that is free floating that does not have a fixed length on the cylinder, so you can see this thing move. So actually, let's take a step back and let's do that, because that's a cool thing to see. We got to go quite a bit back, I guess. There we go. So we're going to draw up. Did not mean to grab that. We're going to draw another one of these arms. Make this all equal. And we're going to put an arm along that. It is coincident. And I'm doing a simple 90-degree thing now, but this could be any range of motion. It really is nice to for all sorts of stuff. Oh, I linked the wrong one to the wrong one. So this one actually comes up here. It's also nice because you can start doing things like, well, let's say I need my pivot point here, and I need a certain dimension here. You might actually draw something and see that your cylinder can't even reach your mechanism, and now you can eliminate something pretty quickly and go, well, clearly I'm asking for the impossible. I need to change something before I spend hours trying to iterate the impossible. I always like preventing myself from iterating the impossible. That is really nice, because that's obviously a huge waste of time. So it's kind of a nice way to explore options, I guess. So now we have this third cylinder in here, which unless, so let's do some dimension. Let's say we want this to be like 2 inches. Ooh, that's too close to see the 2 different arms at first. So I'm dimensioning the lever arm of the extended position. Wow, 2 inches came out dead even. That's cool. And then I will come in and dimension the lever arm of this, which will show up as a driving dimension, and that locks my geometry, but you can right click, come in here and go driven, and now this thing's free floating and is a print again. And what's cool about this is you can use this to go through your range of motion and see, do I always have a big enough lever arm? Because it would be possible to design a system that in the starting and final configuration has a big enough lever arm, but then goes through a point that it doesn't, or goes through a toggle or that sort of thing. So cool. You can see we've made this really simple pneumatic system to go exactly 90 degrees, and we didn't have to guess any numbers. Now there is one cost to this. You would come in at the end and go, God, to my rear pivot, I need a pivot that's 0.4 forward and 2.8 tall. Wow, these numbers are coming out suspiciously clean. I guess I have some geometry that's really simplifying things. Usually that's like 2.8574 and 0.973 and horrible numbers to work with well, not horrible, but not clean numbers. So you do lose control of whatever you didn't originally specify. Like this, oh, but that worked out amazingly clean. God. Well, in reality, this is going to be like 4.789. So we start seeing some uncleanliness, yeah, because that's always something real random with Bimba. So cool. So you have simple systems here. You can do this with arms. You can do this with anything really. Um, Kind of one takeaway here is the trick of doing some angular motion from a pneumatic cylinder. The other takeaway here is you should model motion like this. I've seen a lot of people, including me in the past. I would make all of these parts 3D. I would constrain them, da da da, and use an assembly and move stuff, and then go, wow, that's wrong. Iterate, that's wrong. Iterate, that's wrong. And I spent a lot of time in the that's wrong range, and that was really frustrating. I mean, one, you spend all the time to go 3D, and two, it's just slower to iterate things there. So this is a much better way to do things. Now, what I haven't quite decided on, because I've used just about every way that SOLIDWORKS has to link dimensions to other parts and assemblies, I've yet to get the holy grail of being able to draw a whole robot like this, linking pertinent dimensions to the whole robot. Unfortunately, SOLIDWORKS implementation of global variables is just not quite there yet, in my opinion, especially when you're working with inexperienced people. I've used sketch blocks, and that blows up a little bit. I've shared geometry at the assembly level. I've passed equations at the assembly level, and both of those are just kind of too slow and too tedious. I've passed in sketch blocks of the whole robot and equated dimensions over instead of doing sketch block where you're drawing on the geometry, and occasionally the sketch block blows up, and that just happened once, and now you just broke 400 parts in your robot. So now I'm rambling about. I really hope someone out there watching has a good solution for essentially global variables or linking geometry to one sketch. I'm aware of everything that's out there, I'm pretty sure, but maybe I'm too conservative and don't like something that might even slightly fail. But I've been burned by each of those at least once, especially with inexperienced people working alongside me, so that's tough. But yeah, we'll get back on topic to this. I think this is a great method for doing stuff. Saves you a lot of time with rotary mechanisms. I've noticed a lot of old engineers who used to work in AutoCAD really like it when they see me doing this kind of stuff, maybe just because the screen looks similar for them. All right, so the next video I'm going to do is this, but for a whole robot kind of, and looking at things a little differently. All right, thanks for your time, everybody, and I hope you learned something.